after collision, their velocities will change to final velocities and let it be v1 and v2 respectively. From the law of conservation of momentum, we can say momentum of bodies before collision is equal to momentum of two bodies after collision. After collision, the body may undergo the deviation. It may be along x-axis or may be along y-axis. The algebraic sum of y components before collision is equal to algebraic sum of y components after collision is our next criteria. Hello everyone, welcome to session 3 of chapter 6 Work, Energy and Power. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in today's session, let us learn how to derive an expression for final velocities of two bodies when they are traveling in one dimension and they undergo elastic collision. So, in elastic collision, as we have discussed in our previous session, we know that both momentum and kinetic energies are conserved. So, keeping this point in mind, let us derive now the expression for final velocities of two bodies which are moving in one dimension. Say for example, consider a body A and B which are moving with velocities u1 and u2 before they collide. And these bodies are having masses m1 and m2 respectively. And when they are moving in the same direction, so they collide with each other and their velocity will change. Their velocities will change from u1, u2 to v1 and v2 respectively. So, this is our consideration in deriving the expression for v1 and v2, where v1 and v2 are the final velocities of two bodies when they undergo elastic collision. So, let us derive it now. Consider two bodies A and B which are having masses m1 and m2 respectively. They move in a straight line with initial velocities u1 and u2. So, after collision, their velocities will change to final velocities and let it be v1 and v2 respectively. So, let us assume now the mass of the first body, that is m1, is greater than m2. And from the law of conservation of momentum, as I mentioned before, in elastic collision of bodies, both momentum and the kinetic energies are conserved. So, here from law of conservation of momentum, we can say momentum of the system before collision is equal to momentum of the system after collision. So, what is momentum? Momentum is basically, it is a product of mass and velocity. So, first we have to consider before collision. So, before collision, the velocities of bodies are u1 and u2 respectively. And let us now write the momentum expression for the two bodies before collision. So, it is m1 u1 plus m2 and u2. This is the momentum of body A and the momentum of body B before collision, which is equal to momentum of bodies after collision. After collision, their velocities will change from u1 to v1. u2 to v2. Final velocities of the bodies after collision is v1 and v2. So, hence the expression, the momentum of the system after collision is m1 v1 plus m2 v2, and this is our equation 1. So, now from this, let us bring all m1 terms to one side and let us group m2 terms to the other side. So, transposing this to the other side and this value to other side, we get m1 u1 plus m1 v1 we have here. When it goes to the other side, it will become minus m1 v1, which is equal to, we have m2 v2. So, as it is I am writing, and transposing m2 u2 to RHS, I will get minus m2 u2. So, here taking m1 common from this expression, you can see LHS, I am taking m1 common and I remain with u1 minus v1, which is equal to, from these two taking m2 common, we get v2 minus u2 or u2 minus v2. So, that is our equation 2. So, now as I have told you in the beginning, in elastic collision of bodies, both momentum and the kinetic energies are conserved. So, we have got the expression 1 and 2 from law of conservation of momentum. Now, let us consider the law of conservation of energy. So, it says that kinetic energy of the system before collision is equal to kinetic energy of the system after collision. So, the general expression for kinetic energy is given by half mv square, where v is the velocity. Clear? So here before collision the velocities of bodies are u1 and u2, and hence the expression for kinetic energy of the system before collision, that is kinetic energy of this body is half m1 u1 square, since its mass is m1 and velocity is u1, and this body again half m2 u2 square. So now for a system we are writing the expression, and hence it is half m1 u1 square plus half m2 u2 square, where u1 and u2 are the initial velocities of two bodies before collision, which is equal to half m1 v1 square plus half m2 v2 square, where v1 and v2 are the final velocities of the bodies after collision. So here, so we have a half common in all the terms, and hence we can cancel and we remain with m1 u1 square, bringing all m1 terms to other side plus m1 v1 we have here. When it gets transposed, we will get minus m1 v1 square, which is equal to m2 v2 square already we have here, and taking this to the other side, transposing, we will get m2 u2 square. So here we have grouped m1 terms to one side, m2 terms to the other side. So we can take m1 common in these two, and we can write u1 square minus v1 square multiple of m1, which is equal to m2 common in these two, m2 into v2 square minus u2 square. This is our equation 3. So now divide equation 3 by the equation 2, and it gives, look at this equation, we have equation 3 and equation 2 here. So let us divide these two equations, and we get m1 into u1 square minus v1 square divided by m1 into u1 minus v1, which is equal to m2 into v2 square minus u2 square divided by m2 into v2 minus u2. All the numerator terms we got from equation 3 and the denominator terms from equation 2. Now let us cancel these two terms. m1 gets cancelled, m2 and m2 gets cancelled. Now look at this numerator part, it is of the form a square minus b square, which is equal to a plus b into a minus b. So now let us write in terms of a plus b and a minus b, that is from this expression we have a square minus b square. So we have to write it in terms of a plus b into a minus b, and hence we are getting u1 plus v1 into u1 minus v1, and here also similarly v2 plus u2 into v2 minus u2, denominator as it is I am retaining. Now we can cancel u1 minus v1, u1 minus v1, v2 minus u2, v2 minus u2, and we retain with u1 plus v1, which is equal to v2 plus u2. And now from this expression I can retain v1, because we are deriving the expression for final velocities of two bodies, which is equal to v2 plus u2 minus u1, and this is my equation 4, that is v2 plus u2 minus u1 is my equation 4. So here we got an expression for v1. Let us now substitute this expression in equation 1. What is the equation 1? It is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now we got an expression for v1. Let us write v1 in the place of v1. Let us substitute the terms what we have already derived. So we get m1 u1 as it is retaining plus m2 u2 as it is retaining, which is equal to m1 into, in the place of v1 I am substituting v2 plus u2 minus u1. So this is the replacement for v1 plus m2 v2. This is our equation 1, and just we are replacing v1 by v2 plus u2 minus u1. Now let us write m1 u1 plus m2 u2 is equal to, multiplying m1 with all the terms we get m1 v2 plus m1 u2, plus into minus is minus, m1 u1 plus m2 v2. Now for simplification purpose, let us group all u terms to one side and v terms to the other side. So here we have m1 u1, so writing as it is, plus m2 u2, but here you can observe plus m1 u2 we have. So let us transpose this to the other side, we get minus m1 u2 plus, here we have minus m1 u1, transposing we will get plus m1 u1, which is equal to m1 v2 plus m2 v2. Here you can observe all u terms are grouped to one side, v terms are grouped to the other side. So now let us simplify this. You can see here plus m1 u1 plus m1 u1 we have. So we are adding these two and you can write it as 2m1 u1 plus taking u2 common in these two terms, we will get m2 minus m1 which is equal to, take v2 common in these two terms, taking it out, so we can write it as m1 plus m2. Since we are deriving an expression for final velocities, from this expression we have to retain v2 and we have to bring all the other terms to one side. So v2 is equal to 2m1 u1 plus u2 into m2 minus m1. Here m1 plus m2 is multiplied with v2 and when you transpose to the other side it will come to the denominator and hence we get v2 is equal to 2m1 u1 plus u2 into m2 minus m1 divided by m1 plus m2. This is my equation 5, which means the expression for final velocity of a body B. Now we can write the same for the final expression of a body A by just interconverting the suffixes of 1 and 2. And by interconverting the suffixes we get V1 is equal to 2m2 u2 plus u1 m1 minus m2 divided by m1 plus m2. So these two are the expressions for final velocities of two body when they are traveling in one dimension and when undergo elastic collision. So now let us derive one more expression. So here we are considering inelastic collision. Here we are going to derive an expression for loss of kinetic energy when a moving body collides with another body at rest in a complete inelastic collision. So here we are considering inelastic collision where we can say only the momentum is conserved but not the kinetic energy. Kinetic energy changes from one point to another point and hence we have to find the expression for loss of kinetic energy when one body collides the another body which is at rest. So for this, let us consider two bodies A and B of masses m1 and m2 and they move with the velocities u1 and u2 respectively before collision. So in this scenario, the velocity of object 1, that is u1, has some value but u2 we have considered the body which is at rest, the velocity is 0. So the body B is at rest position and hence the velocity of it is 0, that is u2 is 0. So after the collision, two bodies move together with a common velocity v in the same direction. When the body is at rest, the other moving body comes and strikes it, they both move with the same direction with a common velocity after collision. So let us now consider inelastic collision property where we can say only the conservation of momentum is possible. From the law of conservation of momentum, we can say momentum of bodies before collision is equal to momentum of two bodies after collision, that is m1 u1 plus m2 u2. This is the momentum of the system before collision, which means the sum of momentum of two bodies before collision is equal to momentum of the system after collision, that is sum of momentum of two bodies after collision. Since after collision their velocities will changes to v1 and v2, the expression becomes m1 v1 plus m2 v2 because the actual expression for momentum is mass into velocity. So here before collision the velocities of bodies are u1 and u2, after collision the velocities are v1 and v2 and hence the expression m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is our equation 1. So, as we know that the velocity of body B before collision is equal to 0, that is u2 value is 0, we get the expression m1 u1 plus m2 into 0 which is equal to m1 v1 plus m2 v2. Since I told you that they move with the same common velocity after collision, we can just write m1 v plus m2 v. So, here this entire term becomes 0 and we get m1 u1 which is equal to m1 plus m2 into v. Taking v common, we can just write m1 plus m2 into v. Why it is common? Because after collision both the masses will travel with the same direction with common velocity. So from this we can write the expression for velocity, that is v is equal to m1 u1 divided by m1 plus m2. This is the equation 2 where the expression for common velocities of two bodies. And now we have to derive the expression for loss in kinetic energy. As in case of inelastic collision, kinetic energy is not conserved. observed. So this kinetic energy is lost in the form of other energies. Kinetic energy before collision is greater than the kinetic energy after collision. So the loss of kinetic energy is denoted by delta K, which is equal to kinetic energy of the system before collision minus kinetic energy of the system after collision. So kinetic energy of the system before collision is half m1 u1 square plus 0. Why 0? Because the velocity of body B before collision is 0, and hence the entire term half m2 u2 is the kinetic energy expression for body B. Since u2 value is 0, this entire term becomes 0. So we get delta K is equal to half m1 u1 square plus 0 minus half m1 plus m2 into v square. Why? Because after collision both the bodies will travel with common velocity, and hence we can write m1 plus m2 into v square. But what is v value? V value we have already derived, that is m1 u1 divided by m1 plus m2. Let us substitute that in this equation, and we can write delta K is equal to half common, take it outside, and we can write it as m1 u1 square minus, here we get m1 plus m2. In the place of v, we are substituting this value, and hence we have here v square. So we have m1 u1 divided by m1 plus m2 the whole square. Or we can write this equation as delta K equals half m1 u1 square minus m1 plus m2. Here writing separately the powers. So we get m1 square u1 square divided by m1 plus m2 the whole square. So here we have m1 plus m2, and here in the denominator we have m1 plus m2 the whole square. So 1 m1 plus m2 and m1 plus m2 will get cancelled, and we remain with delta K is equal to half into m1 u1 square minus m1 square u1 square divided by m1 plus m2. Now from these two things you can observe we have m1 u1 square minus m1 square u1. So we can just take m1 u1 square common. We have m1 square here. So taking this outside, we already have half. So taking this outside, this entire term will go out and we remain with 1 minus, here we have m1 square, but I have taken only m1 outside. So I will remain with m1 in the numerator and m1 plus m2 in the denominator. Now taking LCM, so this terms will become m1 plus m2 minus m1 whole divided by m1 plus m2, and all the other terms remains same. So now how can we simplify it further? So we can simplify it further by cancelling m1 and m1, because it is plus m1 and minus m1, and we remain with m2 divided by m1 plus m2. Or we can simply write it as delta K is equal to m1 m2 into u1 square divided by, in the denominator we have 2 here m1 plus m2. So on a whole we can write it as delta K is equal to m1 m2 u1 square divided by 2 into m1 plus m2. So this is the expression for the loss of kinetic energy when the body is undergoing inelastic collision. So let us now move on to the other expression, that is the collision in 2 dimensions. So let us consider the collision of a particle when undergoes 2 dimension. What is the expression for momentum and kinetic energy? So here let us consider 2 bodies A and B, which are having masses m1 and m2, and they have the initial velocities u1 and u2 before collision. So when they collide with each other, when the 2 objects collide with each other, since we are talking about 2-dimensional motion, they may even travel in x direction as well as they can travel in the y direction. So after collision, the body may undergo the deviation. It may be along x axis or may be along y axis, and here we can resolve the velocity of 2 bodies after collision into 2 components, that is along x axis as v1 cos theta 1 and along y axis it is v1 sin theta 1, and here the other body which is deviated to the other side, whose velocity can be resolved into 2 components, that is along x axis v2 cos theta 2 and along y axis v2 sin theta 2. So from the conservation of momentum, we say that momentum of system before collision is equal to momentum of system after collision. Here we have to consider the algebraic sum of x components before collision is equal to algebraic sum of x components after collision. So let us now write this in mathematical form, that is m1 u1 plus m2 u2. This is the algebraic sum of x components before collision is equal to m1 u1 cos theta plus m2 u2 cos theta 2. That is algebraic sum of x components after collision. Similarly, let us now write the expression for the components along y direction as well. Algebraic sum of y components before collision is equal to algebraic sum of y components after collision. So before collision, since the particles will not be traveling in y direction, it is traveling only along x axis, we say that it is 0. The momentum becomes 0 because there will be no particle which will be along y direction before collision. But after collision, they may even travel along y axis, and hence we have resolved the velocity into components. And after collision, we can write m1 v1 sin theta 1 minus m2 v2 sin theta 2. Here we have considered sin minus because after collision, they travel in opposite directions. So that is about law of conservation of momentum, and here we are considering law of conservation of energy. So from conservation of kinetic energy, we know that the kinetic energy of the system before collision is equal to kinetic energy of the system after collision. So general expression for kinetic energy is half mv square, where m is the mass and v is the velocity. So before collision, let us write the kinetic energy of system, that is for both the bodies, that is half m1 u1 square plus half m2 u2 square, which is equal to kinetic energy of the system after collision, and that is half m1 v1 square plus half m2 v2 square, since after collision the velocities of the bodies are v1 and v2 respectively. So motion after collision involves 4 unknown quantities. So what are those 4 unknown quantities? That is v1, v2, theta 1 and theta 2. To calculate the values of these 4 quantities, one of these quantities should be at least known. So this is how we have to write the expressions for law of conservation of momentum and kinetic energy of a bodies when they are in two-dimensional motion. As well as in today's session, we have learnt what is the expression for final velocities of two bodies when they have elastic collision. So in the upcoming sessions, let us learn few more interesting concepts. Until then, keep learning all of you. Thank you.